Welcome back, everyone. This is Professor Herring. In this video, we're going to learn more about liquids. We're going to talk about vapor pressure and boiling points. We're going to talk about phase diagrams and how they relate to heating curves. Then we're going to talk about various properties of liquids, including viscosity and surface tension, cohesive and adhesive forces, and how intermolecular forces are going to affect these properties. Alrighty, let's begin. So, vapor pressure. Vapor pressure is where we have vapor, which is the gaseous form of a liquid, liquid that has evaporated, and it's in equilibrium with the liquid or solid phase. So let's say that we start with a flask of liquid and there's no air or gases up above it. Given enough time and there's energy from the surroundings, we're going to have evaporation that occurs where the gas molecules are floating up above the system, and they're going back into the system or into the water, and they're also escaping. And when the rate of evaporation or escape is the same as the rate of condensation, the rate of them going back in, that's what we call equilibrium. And at equilibrium, there's no net change. So even though there's molecules going back and forth. So think of this like you're going into a store. Okay? I don't know, pick your favorite store. Go to Walmart or whatever. And you've got your in and your out. And if the rate going in equals the rate going out, then the net people inside does not change. Even though people are constantly going in and coming out, the net number of people will not change. And that's what we have for chemical equilibrium, is that there's two opposing processes going back and forth. The molecules are constantly changing, but then there's no net change. Again, our forward rate is equal to the reverse rate. And this happens because our substances are volatile. Volatile means that they will evaporate, and they're going to do so at typically room temperature. And so at a given temperature, a substance that has a high volatility has a high vapor pressure than less volatile substances. And all of this can be explained using the kinetic molecular theory. If we take and look at a given substance at a low temperature versus a higher temperature, we've seen this type of graph before. Remember, these are our Boltzmann distribution graphs or curves. And we see that, and we saw already that at low temperature, there is a higher peak, and a higher temperature, it broadens out. And so if we say, well, how much energy is required to escape? And we just arbitrarily define this line right here. That's a really terrible vertical line, but you see it there. There's going to be a higher proportion of molecules that can escape at the higher temperature because we've shifted our peak and we've broadened it out. And so for a given liquid, as the temperature increases, so does the vapor pressure. So does the amount of gas that can be evaporated. And that's because the kinetic energy is increasing. Higher kinetic energy means that there's more molecules that can enter the gas phase, leading to that higher vapor pressure. So if we have a given temperature, what trend would we expect when comparing substances with different intermolecular forces? Think about that for a second. How would intermolecular forces affect vapor pressure? Well, substances with weaker intermolecular forces are going to have higher vapor pressure. It's because it's easier to break those bonds, or rather the intermolecular forces. And therefore, there's going to be a higher proportion of molecules that have enough energy to overcome the forces if they're weak. Think of it like you're playing Red Rover, and if you're playing with a bunch of old grandmas and grandpas, you're going to be able to get through them really easily than if there's a high, strong bond in between the people. And so these are some curves that look at how vapor pressure is a function of temperature. These are exponential curves you can see, and we can see that it varies based upon the types, the molecules that are involved. So we know that water is relatively polar, ethanol a little bit less so. Diethyl ether looks like this. Dimethyl ether looks like this. And then ethylene looks like that. And so we see is that with these molecules that can exhibit hydrogen bonding or highly polar, those end up with higher vapor pressures as a function of the temperature. It requires a higher temperature to get the same pressure. Okay, if here's the structure of camphor and diphenyl ether, and you can imagine that these, being quite large, have very high London dispersion forces, and therefore that's why it takes such a high temperature to get them to have a high vapor pressure. Iodine is very large as well. I2 weighs somewhere in the 200-ish range of grams per mole, and so it's going to have a very high or difficulty to vaporize it. This line is what we call the normal boiling point. And the normal boiling point is the temperature at which the vapor pressure equals 1 atmosphere. Okay? A substance is said to boil when the vapor pressure equals the ambient pressure. And what that means then is that if you go to a high elevation system, Mount Everest for example, which has a low atmospheric pressure, then it's not going to take as much energy to boil because you don't need to get the pressure, the vapor pressure is high. Whereas if you go to a high pressure system, like within a pressure cooker, in order to get something to boil, you have to put in a lot more energy. And that's how pressure cookers work. By increasing the pressure within the system, it takes a lot more energy to get the water to boil, which means that you can increase the temperature of the water to higher temperatures, and so it cooks the food faster. That's awesome, isn't it? All right, so why don't you try this question? Which substance has higher vapor pressure at 300 Kelvin? Ethanol or water? Pause the video and try this on your own. Welcome back. Okay, so how do we think about this? Well, one way you can do this is just by looking at the graph. So at 300 Kelvin, we can see that ethanol is above the water. Okay? And hopefully that makes sense because ethanol has weaker intermolecular forces compared to a pure substance of water. Let's now turn our attention to what are called phase diagrams. You'd be expected to draw a rough sketch of a phase diagram. And these help us to look at the physical state of a material as a function of pressure and temperature. So the textbook uses the term like a flattened 3D graph, where we can indicate the states of matter on here as well. And those are solid, liquid, and gas. And you need to be able to label these regions on a phase diagram. So hopefully it makes sense that these regions are, that solid is in the high pressure, low temperature region. Remember, solids have lower kinetic energies, and therefore something is solid at a lower temperature. Whereas gases have higher kinetic energy, and so it's going to be in the gas phase at a higher temperature, lower pressure. Liquid is intermediate. You also need to be able to label the triple point. This is where all three phases coexist. They exist at the same time, which is really cool. The critical point, and past the critical point, we have what's called a supercritical fluid. Supercritical fluids are awesome. One such supercritical fluid that is useful for everyday humans, if you like coffee that is, and decaf in particular, is you take carbon dioxide and you convert it into a supercritical fluid by increasing the temperature to very high temperature and very high pressure, and what you can then use it to extract the caffeine from the coffee bean. And that's how they make decaf coffee. Supercritical fluids, it's important to note, once you go past the critical temperature, once you get past this point, there's no going back. You can't decompress it back into a liquid. It's always now going to be this supercritical state. You also have the coexistence curves, and that's what these lines are. These represent the transition between solid to liquid and liquid to gas, or solid to gas. And then the normal boiling and normal melting points, and those are listed there. At 1 atmosphere, you have the normal melting point and you have the normal boiling point. You also need to be able to label the phase changes between these. So melting is from solid to liquid, freezing is from liquid to solid, vaporization from liquid to gas, condensation from gas to liquid, sublimation from solid to gas, and deposition from gas to solid. Let's try a problem here. What's happening to the melting points of water and carbon dioxide as the pressure increases? Pause the video, look over the graphs, and try and figure it out. Welcome back. So the melting point is going to be along this coexistence curve here. Okay? And if you take a really, really close look, you see that the carbon dioxide, if we exaggerate it, it slants off like this, and the water, if we exaggerate it, slants off like that. And so they're going in opposite directions. And so what we see happens is as we increase the pressure, it's going to have different effects on the melting points. So let's just say here, our melting point is right here at 10 oops. Well, all right, I guess we've given it away. So the melting point of the water decreases. We can see that the temperature, which corresponds to the coexistence curve, is lower, whereas here the temperature is going up. And what we see is that the dense phase is more stable under high pressure for carbon dioxide. In fact, the fact that water has a backward slanted curve is unique to only water. Water is the only substance that behaves that way. And this actually accounts for figure skating. How figure skating? That's a really terrible figure skating. I'm not going to try and draw a figure. Let's see here. Okay. Man, there's your laces and the shoe. And I apologize to anyone out there who loves figure skating because that just looks terrible. But that's a figure skate representation. And what you do, the way that figure skating works is we see that it's at a given temperature. The ice is going to melt if we increase the pressure, right? So let's just say, this temperature right here, we increase the pressure, it melts. It goes from solid to liquid. Well, what you're doing is you're putting a large amount of force, i.e. your body weight, onto a teeny tiny area. And as we saw in chapter 12, pressure is equal to force per unit area. And so there's this massive pressure on the ice. And what you're doing is you're putting that pressure on the ice, and it's you're melting it. You're causing it to melt. And then what it does is it makes it so then you can slip and slide and glide along the ice. And very quickly it freezes back over when you skate by. So again, awesome application of chemistry in your everyday life. Now, I don't have a slide for this here, but something to recognize is that with these, if we take and we go horizontally within a phase diagram, we see that we're increasing the temperature. right? And we're increasing the temperature, and then we do a phase change. We increase the temperature, phase change, increase the temperature. Well, you need to recognize that if we take one of those horizontal slices, we create a phase diagram, or excuse me, a heating curve. Okay, where this represents this region, this represents the transition, this represents this region, this is the orange transition right there, and then this last part represents the temperature change right here. And so the heat curves, remember, are the changes in temperature as a function of heat input. And so we can take anywhere. If we were to make a heating curve that goes right here, we'd see that it is simply solid, and then the sublimation process, and then heating up the gas. And so you need to know how to go back and forth between either of those. Okay, let's talk about surface tension and viscosity. These are properties of liquids that arise due to the intermolecular forces that are involved in those liquids. Surface tension is the energy needed to increase the surface area of a liquid, which sounds just like a bunch of gibberish. But we know what surface tension is when we see it. You take a look at these water gliders, and because of the surface tension of the water, they can walk on the water. And that's because the water molecules are attracted to each other. The molecules on the surface of the liquid form fewer interactions. This makes them higher in energy. The surface area is minimized to reduce that energy. Therefore, increasing the surface area requires energy. And so, in other words, these molecules on the top, they form a more durable layer than on the bottom. Where on the bottom, these are lower energy. They're able to move around and move freely. On the top, they can't. And therefore, that creates this tension, and that's what allows things to float on top. Or, in the case of the water strider, to walk on the top. Viscosity, however, is essentially the resistance to flow. And if you take a look at olive oil versus honey, you can see that honey doesn't flow nearly as well. And a higher viscosity means that it's going to flow slower. And intermolecular forces affect the viscosity. High intermolecular forces means high viscosity. And we see that when you increase the temperature, that the viscosity is going to decrease. The reason for this is because you're breaking or disrupting the intermolecular forces between our substances. So those are just some examples of some of the properties of liquids. The textbook has some more information that you should read up about adhesive versus cohesive forces as well. That's it for this video. Thanks for watching. If you have any questions, feel free to ask on Piazza, in office hours, or in recitation. Have a good day.